Welcome to Learn with Bhargav's inaugural session. In this session, we will be covering one of the most fundamental concepts of programming. In today's session, we will be demystifying the intricacies behind decimal, binary, octal, and hexadecimal systems. So, let's get moving. Now, how can we categorize number systems? Just as I stated earlier, we can categorize them into four types. The primary being decimal system. So the decimal system is a system that we've learned through grade one. It is nothing but the place values that we've been learning. So, just for your reference, I'm writing this. We will be covering this later again. So decimal system would be having the base 10 to the power n. So the base is nothing but the place value system. And then moving on, binary system, as most of you must be knowing, binary numbers are either zeros or ones. So we get zero as an output or one as an output. Therefore, we can categorize it as the base 2 system. And then we have the octal system, as the name suggests, is the base 8 system. Now hexadecimal, in the same pattern, we can say that it's the base 16 system. Moving on, I've taken an example over here, a random number, 273.84. Now, all of you must be knowing that 3 is the ones place, 7 is the tens place, and then 2 is the hundreds place. Now, it is a base 10 system, so we must quantify it in terms of 10. So the place values can be rewritten as 10 to the power 0, which is 1, right? And then we have 10 to the power 1, which is 10. And then we have 10 to the power 2, which is 100. As simple as that. Now for zero point 0.8 and 0.04, we can put it as 10 to the power minus 1 and 10 to the power minus 2, which is 1 by 10 and 1 by 100. So we understood the decimal system. So it's nothing but the place values that we've all been learning. But a system in itself is not essential. Rather, the conversion of one system to the other. Now, how do we do that? For that, we must understand the binary system first. So the binary system is exactly like the decimal system, except the place values are to the base 2. So we will be quantifying it as 2 to the power 0, which is 1, 2 to the power 1, 2 to the power 2, and so on until 2 to the power 6. So this is how we will be, representing the binary system. Now, we must convert decimal to binary. That is an essential process. But why are we converting it? Well, let me tell you. So it is because the computer cannot process the data you give as a decimal number. Let's say 273.84 cannot be understood by the computer. So it has to convert it into the binary data type and then process the data. Therefore, it is essential for us to understand the conversion process. Now, moving on with the conversion process, let me just show it to you how it works. I'm just taking 273 for your reference because the decimal points, that is zero point 0.8 and 0.04, will cause an issue or it will make it complicated when we are actually converting. So all we have to do is divide it by 2. Now, when we divide 273 by 2, we get 1, 3, and 6, which leaves 1 as a remainder, right? So the remainder is the most essential in this process. So again, we divide 136 by 2. We can put 6 and then 16, 8, 68. And then we'll get 0 as a remainder, right? Because there's no remainder here. Now 68 by 2, we get 34. Again, we get 0 as a remainder. Again, 34 by 2, we get 1 and then 14, 17. And over here, we don't have a remainder, so we'll put it as 0 again. Now, 17 by 2. Now we will have a remainder. So can we write it as 8 and then we'll have 1 as a remainder, right? And again, we divide 8 by 2, we get 4, which leaves us with no remainder. Again, 4 by 2 gives us 2, which leaves us with no remainder again. And then finally, 2 by 2, we get 1 and then no remainder again. Now, we won't leave the process here. So we will again divide 1 by 2. So this cannot be, divided. So when we take 1 divided by 2, we get 0 in the quotient and 1 as a remainder. So we must put that remainder up there. So eventually, this would be our binary value of 273. All right, so let's get moving. Now, we have understood how to convert decimal to binary system, but we must also understand the reverse process. Now, how do we convert this entire value into a decimal number? Let me just show that for you. All right. So I've just taken the value over here. Now, as I told you, the place values are very important. Now, in the reverse process, the place values are extremely important, let me tell you. So, since it is 2 to the power 0, 2 to the power 1, and so on, we must multiply all of these digits with their corresponding place values and add them together. So, it is the summation of the product of the digit and the place value, and then so on. So let us just write it. That is equal to 2 to the power 0 into 0 plus 2 to the power 1 into 0 plus 2 to the power 2 into 1 plus 2 to the power 3 into 1 plus 2 to the power 4 into 1 plus 2 to the power 0. No, sorry, 2 to the power 5 into 1. No, into 0 plus 2 to the power 6 into 1, which is nothing but 1 into 0 plus 2 into 0 plus 4 into 1 plus 8 into 1 plus 16 into 1 plus 32 into 0 plus 64 into 1. So what do we get eventually? That is equal to, uh, let me cancel this out, cancel this out, cancel this out. So it's 4 plus 8 plus 16 plus 64, which is equal to um, 92, right? It is equal to 92. So when we ask what is the decimal value of this binary number, we get 92. It's as simple as that. Now, as you may be, seeing, it is all about mathematics. So computers is nothing but a derivation of mathematics, after which we came up with so many programs, logics, etc. So math is essential in computers. Now, the octal data, can we represent this with the base 8? As I told you earlier, when we are using another data type, we must replace it with the corresponding base. So it's supposed to be 8 to the power 0, 8 to the power 1, and 8 to the power 2. Now let's again convert this into decimal. The same process yet again. So it will be 4 into 1 plus 2 into 8 plus 1 into 64. That's simple. So we make it 4 plus 16 plus 64, that's equal to 84. All right, great. Now, hexadecimal. This is quite interesting and quite complicated for those who don't understand it. So, it is quite a different number compared to what we've seen over, compared to what we've seen over here. This value, which is just numbers, even this is numbers, and even this is the number. But when we come here, we're getting letters over here. Let me tell you why. So hexadecimal is to the base 16. So let me just write down all the values. We start with 0, all right? 1, 2, 3 until 9. And then after this, we have gaps. Why? We can't use 10 because it is the base, because it is a base 10 system. That is nothing but the decimal system. So therefore, we must replace 10 with some other value. Therefore, they have taken letters. They made it A, B, C, D, E, and F, where A represents 10, B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. So let me just convert this value into decimal and let's see what we get. It's just two values. So we have 3 and F. Again, can we put it as 16 to the power 0 and 16 to the power 1 because hexadecimal is the base 16, right? So that is equal to F. What is F over here? F is 15. 15 into 1 because it's to the power 0 plus 16 into 3, right? It's equal to 15 plus 20, okay, plus 48. And what do we get here? 63. So this is our decimal value eventually. Right. Great. So I would suggest that when you're converting hexadecimal to binary or binary to hexadecimal, don't do it directly. Rather convert hexadecimal to decimal and then further convert that to whatever you want. Because it is a less complicated process than when you're doing it to either of them. So this is it. Thank you for watching.